So yeah, thank you so much for the introduction. My name is Farah, and I'm a systems engineer right now on the Perseverance rover. I've been at JPL for just a little under 7 years, and as was mentioned in my intro, I've done a lot of jobs during that time, but my main ones is somehow, even though we explored a solar system, I've been exploring Mars for the past 7 years. So I worked heavily on the InSight lander that landed on Mars almost 2 years ago now, and also worked on the companion mission, which was the Marco CubeSats, which were a pair of small spacecraft that did telecommunication relay during the entry, descent, and landing phase of that mission. So I've been on Perseverance for almost 2 years now, and specifically I'm a mobility systems engineer. So that follows pretty well from Dr. Verma's talk earlier on. So she obviously drives our rovers, and I part of the team that does all of the testing ahead of landing to make sure that our system, that our flight system, that our rover itself is built properly so that we can drive and survive the environments on Mars. So today I'll be talking about Perseverance, kind of giving you a larger overview of the Perseverance rover. There is a talk, I believe, on Sunday that will focus on the science that the rover will be doing. So I'll be really focusing on the engineering part of it, how we build a rover like this, what does that look like, and what are we up to right now as we're on our way to Mars. So I really love this picture here because it shows you sort of like the evolution of Mars exploration over the past 20 or 30 years or so. So it obviously started with Pathfinder, and then in the 90s we had the Mars exploration rover, sorry, early 2000s we had the Mars exploration rovers, right? Obviously Spirit and Opportunity, which, you know, these missions really paved the way for our ability to not only build rovers that can survive on Mars, but also operate them. Then in 2012, Curiosity came along, and I was actually a mere intern in the summer of 2012. That was my first internship at JPL, and I saw, you know, the team landing Curiosity on Mars, and that's really how I fell in love with JPL and how I decided that this was the place for me, right? To see engineers basically achieve what seems impossible, like they landed a rover on a sky crane on another planet. Who does that, right? Apparently JPL does. And so how would you not want to work for an institution that's able to achieve that? And I still remember those first few weeks on Mars. I was still on lab and got to see sort of it all happening, and I was seeing this, this new area on Mars. So now, of course, we have a Perseverance rover that's going to be landing in February of 2021. And it's really standing on the shoulder of giants, right? It's an upgrade from Curiosity. It looks a lot like it. It's a little bit bigger, a little bit heavier, obviously a little bit more high tech. But it's building on what we learned from Curiosity. It's obviously improved a lot. And it's also, in addition to continuing Mars exploration, it's actually paving the way also for human exploration eventually on Mars. And I'll talk about that in a few and talk about a couple of the instruments that are going to achieve that. So you've probably seen this more than once before, but this is what Perseverance looks like. Some of the major upgrades that we have from Curiosity, we obviously have brand new wheels, a new tread pattern. It's a little bit different material, slightly different wheel size. That's a lesson learned from some of the driving and the issues that we saw with the wheels on Curiosity, and I'm sure you heard about that in just a talk before this. We also have a brand new arm and end effector here that's much heavier than what we had before, with a new set of instruments on there. And then within the belly of the rover, the most important upgrade, right, is that we have a sample caching system, because the goal of Perseverance, one of its main goals when it explores Mars, is that it will collect sample cores that it will then seal and leave on the surface of Mars for a subsequent mission to go get. So we'll be traversing large distances on Mars across a variety of terrains, caching samples, and then eventually leaving that cache on the surface of Mars as a stepping stone for what would be eventually the Mars sample return architecture and mission, where we would send another mission with possibly a lander and a rover to pick up those samples, launch them off of the surface of Mars and bring them back to Earth. Now, what kind of samples are we looking at? Well, Perseverance really is doing astrobiology. It's looking for evidence of ancient life on Mars. So there's belief, obviously, that Mars may have looked like Earth billions of years ago. And billions of years ago on Earth, you know, we're talking about microbial life. And so we're looking for that kind of equivalent life on Mars. And obviously, like any other good rover, we're also doing a lot of geology, and we're landing in a very interesting area in terms of geology because we're landing in Jezero Crater, and especially in a river delta that has, you know, we know already has incredible geology that we're going to be exploring. But as I mentioned, the fourth goal here for Perseverance is also to prepare for humans. So let me talk a little bit about the instruments that help us prepare for that, since I know that the rest of the instruments will be covered in a future talk that you'll see this weekend. So you see here a little bit of a blown up view of the interior of the rover, and it points out all of the instruments that we have on board, but the ones that are helping us prepare for humans are these three over here. So we have a weather station. We've actually had weather stations on most of our Mars missions. InSight had one, Curiosity had one. So wind sensor, temperature sensor, pressure sensor. And the idea here is that we're collecting an idea of the weather on Mars in different areas, in the different locations that we've been landing, in order to build sort of a more global map and a global understanding of what weather looks like on Mars. We also have RIMFAX here, which is a ground penetrating radar. So as we're driving on the surface of Mars, we're going to be radiating out of that antenna to understand the structure below the surface of Mars, which is important if we eventually want to bring humans there, not only in terms of understanding what's below the surface, but also how we might want to build on the surface, or what kind of structure that we're talking about here. But my favorite instrument here is MOXIE. Oops. Oh, I need to only click one button. And MOXIE right here in the, this is really annoying. Let me see if I can fix this. MOXIE right here in the middle of the rover is my favorite instrument. It's actually an in-situ resource utilization technology demonstration. And what MOXIE is going to do is it's going to take in the atmosphere from Mars. It's a really thin atmosphere, about 1% of the Earth's atmosphere. There is no oxygen. It's not really breathable. But what it's doing is that it's separating molecules from the atmosphere and extracting the oxygen. So what we're demonstrating is that we can, with this instrument, produce oxygen directly from the resources that we have on Mars, which is the atmosphere. Now, MOXIE is not producing a whole lot of oxygen. It's producing about a sixth of the oxygen that a normal human would need in a day, so it's not all that much. But the idea there is that if we can demonstrate that it works in that small of a package, then we could land in the future a bigger version of MOXIE that could potentially produce more oxygen and prepare oxygen for humans as they were exploring on the surface of Mars, rather than them having to bring their own oxygen to survive during that time. So let's look a little bit at the mission timeline here and broadly what the events are there. So, so the mission, you know, the idea for the mission has been around for a long time. We've been talking about a potential Mars sample return, obviously, for decades. But really, the idea started coming together for the Mars 2020 mission around 2012, 2013. It took until November of 2018 for us to select our landing site. The reason for that is because it's, you know, we go through an entire process when selecting a landing site. Scientists will come together as a team. They will pitch to each other different areas to land on, and eventually they settled on Jezero Crater. Jezero Crater is special because it's an old lake bed that is dried out, but it had an inflow and an outflow, so it had a river running through it. And you can clearly see in the area that we're targeting that we'll be landing in the delta of that river. Which is interesting in terms of astrobiology. The build of the rover took about 6 years. So it started around 2013, 2014, and then obviously it ended in about February of 2020 because we launched on July 30th of 2020. We're currently on our way to Mars. We're about a third of the way there right now, and we'll be landing around noon Pacific time on February 18 of 2021. Starting surface operations pretty much right away. If you've seen the landing of Curiosity, you'll remember that we land wheels down and ready to go. We'll have the the mast will need to be deployed, and that happens in the first few days. And then the first drive will likely happen within the first week or two of landing. So we definitely don't waste any time once we get to the surface of Mars to get started on our goals. So I want to focus here on this design and build phase, because this is really part of the core of what I do. I work on the flight system team, and so I helped test the rover in preparation for the launch, and I'm still actually testing it, and you'll see how I do that later on as well. So this is one of my favorite videos. Let me just mute it so I can talk over it. It gives you a little bit of an overview of what JPL looks like, and also what it looks like in the room where we build these rovers, because we built them all in the same room, the same clean room at JPL. So what you're seeing here is a cruise stage and the housing in which I'll make me back up here and go a little bit more slowly. So this is the cruise stage. That's what's attached to the housing that the rover is in right now. It has solar panels on it, and also all our propulsion system. And here you're seeing the housing, but you'll see it again. This is the, hold on one second, a little bit finicky today. So you're seeing the cruise stage, and then here is the descent stage. So what you saw there is that sky crane that will drop us off on the surface of Mars. And so that's what's attached, essentially, that's the jetpack that's attached to the rover. Here you're seeing the cruise stage again, which is the housing for the rover, and you're seeing it being all assembled. And one of the challenges when you're assembling something so big is transporting it from room to room. It's quite the endeavor. It's so heavy and huge and expensive, obviously. So it's quite the endeavor to get it across lab and do its different tests. So what you're seeing here is kind of an overview of the type of testing we do, and I'll get into some of the environmental testing as well. This is how we build the wheels and assemble it. So it's basically a very clean machine shop, right? Like in a garage, like we build everything on house. Once it's built, we do all of our inspections. You'll see that we do functional testing where we move every component, make sure that everything is behaving as expected. And it takes an army, right? There's people all over. Whenever we do anything, there's someone else watching. And I always find it funny when you see, this many engineers, and you'll see in one of my next videos, sort of watching every motion on the rover, because it's the first time that we're doing them. And then we'll get to Mars in a few months, and we just let the rover do whatever it wants to do on Mars, which I find pretty funny to imagine that a little bit. So here's an overview of what the spacecraft assembly facility looks like. So I mentioned over here is the cruise stage. Here's that jetpack I mentioned, and then the rover is right here. And this picture was probably taken around, I would say probably around January of this year, maybe a little bit earlier. But this room over here is where all of our internal missions are built. So you can see on the back wall over here are all of the mission patches for the missions that were built in that room. And it's quite special when you're in that room or when you're testing anything in there, because that room has so much history. It's basically the core of JPL. It's where we build all our missions. It's where we've been building them for over 50 years. And to think of all of the history, all of the scientific discoveries that started by something being built in that room is pretty incredible. And I always love sharing this picture here, because the folks in this picture are actually some of my friends. And for me, I've been at JPL, I've only been there 6-7 years. I was in grad school before then. And it's so cool to be able to say that my friends and I are building a rover that's going to Mars. Right? I'm always surprised that I get paid to do this, actually. But it's so incredible to be able to share that and to say that, like, yeah, we've literally put our blood, sweat, and tears into building this rover. So I think this picture really encompasses that feeling that I have pretty much every day when I work on this, knowing that a part of me essentially is on its way to Mars right now. I want to share another video with you that goes into a little bit more of the detail, let me mute it as well, of the testing campaign that we went through. And so the rover assembly ended around August, early September of 2019. And then from September to December 2019, we went through a full testing campaign where we put the rover through everything, all of the environments that it might see on its way to Mars and on the surface of Mars. So you see here the whole thing being packed together. You saw it on a spin test, which is how we get the mass properties for the rover. Here we're going to shake the rover in this particular test, which is the scariest test. We shake it in the environment that it's going to see during entry, descent, and landing. Here you're seeing the testing for the mobility system deployment. As I mentioned, it gets deployed as we're landing on the surface of Mars. Now here this moment right here is the first time that the rover stood unassisted on itself. So it's the first time that we actually put the rover down and it was on its wheels. And then one of the biggest tests that we do is an environmental test. So we have a special chamber, which is a thermal vacuum chamber. And we can do two things in that. We can do a solar test where we have special lights that mimic the solar environment. That helps us measure things like our thermal environment, make sure that all of that is within tolerances. And then we seal that room, we'll pull out a vacuum and we'll actually backfill with basically a Martian environment. And we put the rover through a series of tests that mimic a day on Mars. This is the full end-to-end test of our sample caching system that I mentioned. So that system is pretty complex, right? We have to take the sample with one arm, put it in our caching system, transfer it to another arm that you're seeing here. So that's a second smaller arm inside the rover that then passes it from instrument to instrument before sealing the sample. And finally, my favorite test, because I'm part of the mobility team, is a drive test. And I'll show you another video here with a little bit more detail of that day. And actually, I'll do that right now. See if we can get there. So this is a video of the first drive. And that happened in mid-December of 2019. That was one of the last tests that we did before shipping the rover to Cape Canaveral. And I was part of the team that this was our key test, right? This is the one drive. This is when the rover gets its driver's license, right? This is the one drive that we do on the flight vehicle. So we built what we call a little dance floor. We had a ramp. Obviously, this is one of the cooler tests, if I do say so myself. So we had a lot of visitors come and see what's happening. And basically all we did is we made the rover do some twists and turns. We made it go over a ramp. And here again, you see all the engineers watching this, right? And I laugh because, this was our first drive. And this is the only drive actually that humans are going to see. The next drive that we're doing with the rover is going to be on Mars, a week or two after we land. So, that was pretty exciting tests for us to do and gave us a lot of really good data. So soon after that, in terms of timeline, is when we shipped to the Cape. So we shipped in early February. This is one of the first pictures once we got to Cape Canaveral when we did our final mass properties. Don't worry, we removed all of those amostat coverings. The wheels are not covered on their way to Mars. But one of my favorite pictures is this one over here. So you're seeing Perseverance here in its cruise stage. And here is the payload fairing. So that's the fairing that goes on top of the rocket. I always laugh and think of this is pretty much the Amazon packaging of launching rovers to Mars, considering how small it is and in its fairing. And the reason why that is because we use commercial rockets, right? And so these rockets are used typically to launch commercial missions to low Earth orbit, much bigger spacecraft. We just needed the propulsion. We needed the boost, but we didn't need as much of the volume. So that's why it looks like this. And obviously launch day went off without a hitch in the early morning of July 30th, 2020. I was actually watching from home because of COVID. I didn't get to travel to Florida. It was kind of a safety choice, but I got to watch it with my entire team at home, which was really, really cool. So what are we doing now? We're on our way to Mars. We're about just over a third of the way there. I can assure you we are not resting on our laurels. And I know someone asked this question earlier about how we're testing. Well, we have an Earth twin of Perseverance. She's called OPTIMISM. And she's pretty much the exact twin of Perseverance. Right now, she doesn't have her arm installed. That's coming up. But she has our entire mobility system and the mass and all the instruments up there. The only difference is that she does not use her radioisotopic source to drive around. Wouldn't be the safest thing to do. We actually just have a long cable plugged into the wall. So it's a little bit of a pain when we do our tests. I have to carry the umbilical around, but other than that, she's pretty much the same. And I've gotten the opportunity to play around with OPTIMISM in what we call our Mars yard. It's essentially a big sandbox for the past few weeks. Actually, I've been doing the core of my testing this month. So we're testing everything that is software related. We can test now, and then if there's any issues, we can always do a software update. That's the advantage of software, really. So we've been putting her through all of the types of terrains and conditions and off-nominal conditions that we might see when we get to Mars, so that we know how the rover will behave, but also how we should react. Now, one of the issues with Optimism, though, is that because she's about the same mass as Perseverance, she's not the same weight as Perseverance will be on Mars. So in terms of when we're doing anything that's driving related, when we're talking about traction or going up on slopes, it's not very accurate. It's not an accurate model. And so we have another rover called Scarecrow right here. And Scarecrow is a third of the mass of the Perseverance rover. So it has the same weight here on Earth as Perseverance will have on Mars. So we do a lot of our detailed mobility testing, anything that has to do with going over different terrains and things like that on this particular rover. So you can see that it's a pared down version. It's very mobility centric, and it has sort of like, it doesn't even have the real brains of the rover. It has a laptop on top that mimics a lot of the, that has the processing that the rover has on board. So that's how we do that testing here. So finally, I just want to leave you with this picture before we get to the question and answer, because one of the things that I always want to emphasize with these big missions is that it really takes a village. And there's probably over 1,000 people at JPL that have worked on this, more than 2,000, I'm sure, across the world. It's really an international collaboration. And this is all of us going to Mars, right? This is not only for us, but for the public and for the scientific community. So for me as an engineer, it's always great to know that I'm part of something that's bigger than myself. And that's really why I love doing what I do, and basically with these Mars missions, because technologically they're so incredible. And only with these great teams can we achieve such big feats. So I'll just leave you with a page of resources, places to go learn more about the Perseverance mission, Twitter accounts to follow, things like that. And I'll open it up for questions, so we're about 5 minutes to do that.
Thank you, Dr. Alibay. That was excellent. We do have a few questions from our participants. Peyton asks, what was the hardest or most complex instrument to build?
Ooh, so I wasn't part of the team that built the instruments, of course, but I think, you know, if you count the sample caching system as an instrument, which it's part of it, right? I would say I mean, that's probably the most complex part of the rover as a whole, right? It's the one thing that is completely brand new. And there are so many, literally so many moving parts in that system. And not only that, but it has to meet planetary protection requirements, for example. So for sure, that entire system, I mean, the team that built that, it's almost as complex as the whole rover itself. So that's really the biggest achievement on this rover.
Sorry, I wasn't unmuted. Adam asks, what drove JPL to consider a sky crane mechanism for final lowering to the Martian surface, and how is it tested prior to launch?
So so it's a little bit of a history there, but basically we had on the MER rovers, we were using airbags essentially for landing, so parachute airbags, and that was our system for landing. And what happened with Curiosity, and again, it's less my specialty, but I know a little bit about it. So what happened with Curiosity is because of the mass of the rover, we just couldn't use the old landing systems that we had, right? And remember that one of the challenges with Mars, it's not like the moon where the gravity is really low. Mars still has a decent gravity. It also has an atmosphere. So that kind of restricts us as to how we can land on the surface of Mars. So we use parachutes, but the sky crane was really, I mean, I'm pretty sure that the stories I've heard is that, you know, someone came up with a concept on the back of a cocktail napkin and thought, well, what if we do this? And it's inspired a little bit from things we do here on Earth. So they did have some, and so for Perseverance, we're relying heavily on heritage from the Curiosity mission. So there was some testing, some drop tests that were done for that. And a lot of it is analytical, right? That's one of the challenges. That's why landing on Mars is so hard, because we can't really test the full system end to end here on Earth, because we just can't replicate that environment. Gravity is really hard to replicate, and so is the atmosphere. So, so that's why this is challenging. But yes, there's piecemeal testing. Obviously, we're relying on heritage here, and a lot of analysis that goes behind that.
That kind of leads right into a question from Kaj. She asks, what part of the rover's operation is hardest to model and test accurately here on Earth?
So yeah, so I mentioned a little bit with the landing. Obviously, that's probably one of the hardest things on the surface of Mars when we think about operations. Again, I think the environment is a little bit different, and things like telecommunication, right? Like we did what we call an EMI/EMC test where we test out the radios, but the concept of a rover talking to an orbiter and the orbiter transmitting the data back to Earth, it's something that's quite complex. Now, we've been doing it on Mars for decades, so we have experience. But it's always a challenge, actually. And one of the things that we're doing right now as we're on our way to Mars is that we're preparing for operations by doing what we call operations readiness tests, where we'll mimic a week of operations on Mars. And it's always challenging. We have what we call test as you fly exceptions, so things that we can't mimic on Earth. And we take those as needs and we try and work around them. But definitely testing that end-to-end system, even with the replicas of these rovers that we have on Earth, can be quite complex and challenging.
All right, thank you. Last question here from Kai. Will you have an opportunity to work on another rover in your career, or do you stay with this project through its full operational life?
Hopefully I will. So I was part of the team that helped build the rover. I will actually be part of the operations team for the rover as well. So I'm quite excited about that. But I don't necessarily have, what usually happens is folks will stay on for the critical part, and then a subset of that team will stay on for operations long term, and then we'll move on to other missions and maybe keep working on this half time and work in other places another time. So for example, even on Perseverance now, I work with people who still work on Curiosity part-time and bring a lot of that knowledge to the next rover. So absolutely, I hope to continue working with this rover for a little while at least. And then I really hope that in my career, I'll get to work on another rover, perhaps the rover that would go get, perhaps a system, however it ends up being, that would go get those samples back from Mars and bring them back to Earth.
Excellent. Thank you so much, Dr. Alibay. That was an excellent presentation.
Absolutely. Thank you for having me.
Yep.